third course outcome is that polymeric materials. In that, so far, what you have seen is that crystalline nature of polymeric material, right? So no polymer is 100% crystalline. Part of a crystalline material is part of a polymeric material is amorphous one. So generally, we call all polymeric materials are semi-crystalline polymer. In fact, you can, if you want, you can have 100% amorphous polymer, but it is very difficult to get to reach 100% crystalline polymer. So crystallinity, the concepts on crystallinity we have seen, and we have seen also some mechanical properties also. What we'll do is that we'll quickly refresh the concepts, and again we'll come into the business, right? We'll come back to the business. Okay. Okay, guys. Okay, so what I'll do is that please, a few of them are still there. Ajay, Arun, and Mukesh, please switch off your video, right? Now, what I'm going to do is that I'm completely taking control of all annotations. Basically, I'm going to sit in the driver's seat of Zoom app, right? I will completely control all these things so that good. Okay. Disable participant annotations so that they won't write anything. Somebody's writing hi, and annotate clear. Yeah, clear all drawings. Fine, we'll start. So another property is that modulus of elasticity. If you look at it, the modulus of elasticity can get it from the slope, basically, right? You can get it from the slope. If the slopes are varied, then your modulus of elasticity value gets changed, right? And the area under this curve, that is in stress strain curve, is your toughness. The area under the stress strain curve is your toughness, basically. It is that how the toughness is defined generally is that it is a ability of a material to absorb energy before it breaks or gets fractured. Once again, the toughness of the material is defined as the ability of the material to absorb the energy. So if you do some work on that polymeric material, right? So how much energy it gets absorbed because of the external pressure or force. So the maximum value is that, right? Before it breaks, how much energy it gets absorbed is your toughness, basically. So far, what we have seen is that we have seen tensile strength, yield strength, now modulus of elasticity, and toughness. If you look at the next graph, next PPT, right? Okay. So y-axis is your stress and x-axis is your strain. And so if you look at this blue line, right? If you look at this line, right? So you know that the slope for this is very high, right? So your basically your modulus of elasticity is very high. It is very strong material. And if you look at that, area under the curve is very, very less. The area under the curve is very, very less. So your toughness is reduced. If you look at the pink color, right? Okay, the slope is very less. So your modulus of elasticity is very low. It's not strong. And the toughness of material is also very low because the area under the curve is very small. If you look at that red line, right? Okay, the slope is also comparable, and the area under the curve is also very high, right? And the area under the curve is also very high. So this type of material shows both toughness and strength, right? These materials are very strong and very, very, very tough. Okay, so these are the main four properties. With this, we'll get into that. We'll study that behavior of polymeric materials, right? Especially, we are going to focus on mechanical properties only. Okay, the response of this is Okay, this graph you have already seen. Just will recap it. And this is basically a stress strain graph, and this is for three different materials. One is that it's a brittle material. Now I call it as an A, and another is that it's a plastic material. I call it as a B cow, and third one is elastomer material, right? I call it as a C, right? Basically, brittle material is that it is your thermoset polymers. Basically, it is a thermoset polymer, that is your type A material. It's a thermoset polymer. So if you give a stress, there is negligible strain is induced in the material. So when the strain is very less, and you can see that there is no plastic nature of a material, only elasticity is there. That is up to 60 megapascal. If you give a stress of 60 megapascal, there is a small strain in this material. But when you leave it, what will happen is that again it will come back to its original position. So there is no permanent deformation is there, only have a temporary deformation is present in the material. So if you go beyond 60 megapascal, what will happen is that your polymeric material fails miserably, right? It is a brittle. There is no plastic nature is there. This is a type A material. Basically, all your thermoset material, for example, you take epoxy, you have a polyurethane material. These are all cross-linked material. Epoxy, polyurethane, and backlight, phenol formaldehyde. These are the good example for a brittle polymer material. When you look at it, type B material, right? Type B material is a plastic material. You can see that up to 30 megapascal, right? Up to 30 megapascal pure. If you apply a stress of 30 megapascal, the material shows elastic behavior. Thereof, what will happen is that there is a plastic deformations takes place and comes out, right? And finally breaks after a certain strain. So there is a considerable amount of strain is present in this material, right? These are from near to zero point 0.5 mega, zero point 0.5 strain to say 4 strain, right? This is completely, it shows a plastic nature in this region. It's a completely a plastic nature of a material. Before that, up to 30 megapascal of stress, it is a elastic nature of material. So when you remove stress, when you are giving a stress of 30 megapascal to a material, and when you remove the stress, what will happen is that because of elastic nature, the polymer come back to its original positions. That is, no deformation is there, no permanent deformation is there. But when you keep on increasing more than 30 megapascal, what will happen is that, right, it reaches basically this is your yield strength, right? I call sigma y is your yield strength. The unit is in megapascal, and after that your plastic deformation starts, and the metal starts straining out much more. And finally, right after certain strain, say for example this position, right, your material fails. Next type of material is that it is your elastomers, right? So if you give a very small stress, that amount is good enough, right? In order to have induce more strain in the material. This type of material is called, it is an elastomer, basically rubber type material, gel type material. These are all elastomers. These are very good examples for elastomer material. For a plastic material, say polypropylene, polyethylene, polystyrene, right? These are all very good examples for a plastic material. So in this course outcome, we are going to focus more on plastic material rather than a brittle polymer or a elastomer, right? We are going to focus only on plastic material. That's plastic polymeric material. So, right, I've already told that, right? Okay, there are four mechanical properties. Out of that is that uh, right, this is your yield strength, okay, and this is your tensile strength, right? This is your yield strength and this is your tensile strength. These are the two mechanical properties generally for the applications. Any engineers, they want to design any component using polymeric materials, they will look for these two properties, right? So one is that yield strength and another is that tensile strength. This is that. So yield strength is that just right where your elastic behavior stops, and tensile strength, what it indicates is that, above tensile strength, right, the material gets fractured or material fails. Okay, please keep it in your mind. Yield strength and tensile strength, these are two important properties. Okay, and if you look at it, right, for example, if you take some polymers, your tensile strength is much greater than your yield strength, right? Your tensile strength is much greater than your yield strength, right, for certain materials. All right, so your graph may be like this, right? Your graph may be like this. Your graph may be like this, right? And in some materials, right, your yield strength is, right, your yield strength is much more greater than your tensile strength, right? Your tensile strength, right? So that may be the case. Maybe it may be like this, right? This may be like this, right? This is your tensile strength. This is your tensile strength, basically. Okay, we'll see some example for this, right? Okay. Uh, so now, please carefully look at the table, right? Okay, it gives types of material, polymeric material with specific gravity, tensile modulus, tensile strength, and yield strength and elongations. Now let us focus on tensile strength and yield strength, right? We have talked about. For example, if you take a material, right? If you take a material, for example, nylon 66 and the polyester. If you look at it, nylon 66, your tensile strength is much greater than your yield strength, right? Your tensile strength is much greater than your yield strength in case of nylon. In case of your polyester, right? Okay, your tensile strength is much lesser than your yield strength, right? The range of value, what it takes about that, right? Depends upon your molecular weight, depends upon your molecular weight, nature, and percentage of crystallinity in this. Okay. So these are the classic example. Now we'll look at the structure for a nylon and a polyester. Please keep it in your mind, right? Nylon tensile strength is much greater than your yield strength. That is, look at it here, right? What yield strength tells is that, okay, your elastic nature ends much before when compared to your polyester. Your elastic property of a nylon ends much before or the elastic property of a polyester. Please keep it in your mind. And next is that, right, what tensile strength indicates is that fracture, right? So here what happened is that you see that, right, your tensile strength, if you look at the tensile strength for nylon is that it is a 75, right, when compared to, right, when compared to polyester, right? You take a clear, I will clear all the things, right? If you look at it, tensile strength of nylon, right? If you look at the tensile strength of a nylon and you look at the tensile strength of polyester, right? So this is much higher, right? Our nylon is much higher. In the case of yield strength, right, your polyester is much higher, right? So, okay, what I'll do is that I will mark only the higher value so that it won't give any confusions, right? Okay, this is your higher part and this is your higher part, right? So tensile strength, what it tells is that, right, your material thereafter it gets going to collapse, right? It gets fractured or it deformed permanently. So the value is 75.9. It is much greater than it's 48. But other way, the yield strength is much lower. So this is how you compare your mechanical properties of a nylon and polyester, right? So generally, okay, people they won't mind having a permanent deformations, right? But I need right, I need a material, polymeric material, which has to withstand higher tensile strength. Means then you have to go for a nylon, right? Otherwise, no, I'm much bothered about uh, yield strength, right? I'm much bothered about the elastic property, right? I don't have any permanent deformations in the material, because I'm going to use this material in the clearance between any two mechanical components. What will happen is that then if you give a stress, then you won't have any clearance, because there is a permanent deformations takes place. In that case, you should not choose your uh, you should not choose your this one nylon material, right? You can choose your polyester material. That's much better. Okay, and we'll see the structures, right? That will give some insight why it is that. So this is a structure. Okay, nylon, right? Nylon, it is a linear chain. Nylon 66 is basically it is a linear chain. And when you compare with the cellulose, right, it is a ring shape, right? Benzene ring is there, right? It's basically it's a ring structure, basically, right? So when it form a crystalline, right? For this is a nature of formation of a crystallinity is very high. Nature of formation of a crystallinity is very, very high, right? Crystallinity is very, very high because it is your linear chain is there, right? You have a linear chains, right? You can form a crystalline, right? Crystalline regions, right? This is very high. But in this case, in the case of cellulose, right? The percentage of crystallinity is much, much, much lower. This is the case, right? And you look at that, right? If it is a ring, the cellulose is in a benzene type of ring. It's a ring structure, so it is very difficult to open the structure, right? So this is that. When you have a crystalline, then you need to supply more energy to have a uh, elastic. You need to have a elasticity, right? Okay, right. So you look at it, right? Okay. So what happened is that, right? Okay, the tensile strength is very high in nylon because of, right? It can have more uh, percentage of crystallinity in this material that is not allowing to material to break it. Where why you are getting a low yield strength is that the amorphous of nature of this material in that nylon, right, gives a plastic nature of a material. This is that, but the strength is coming from a crystalline pot. The tensile strength is coming from a crystalline pot, and the amorphous nature or the molecules uh, conformations, right, tells about that your yield strength. Okay, so molecular conformations like ring structures, right? It will give a high yield strength, and crystallinity behavior will give you a tensile strength, right? So this will give some insight about the polymers. So when you compare the mechanical properties of a polymer, say for example, modulus of elasticity, tensile strength, and elongations, right? Okay, so we already told that, right? The value lies between 10 megapascal to 4 gigapascal for a polymer. If you take any polymer, right, the value of a modulus of elasticity, right? I told you, know, in stress strain curve, there is a slope. That slope tells you about the modulus of elasticity. The values of polymer for this is that is from 10 megapascal to 4 gigapascal. So this is much lower when compared to the metals. The minimum modulus of elasticity for a metal is that it's a 50 gigapascal, where it is no way, polymer has no way close to modulus of elasticity of a metal. And also tensile strength also like that. It is tensile strength for a polymer is that you take any polymer, okay, it will be in the zone of 10 to 100 megapascal. But for metals, it is hundreds of megapascal to several gigapascals, right? It is in a gigapascals. There is no way of comparisons of tensile strength and modulus of elasticity, but you should have some idea about the strength of or the mechanical properties of a polymer in compare with metal, right? And guys, we have only 10 minutes left. Anyway, right? If the session ends abruptly, then what we'll do is that I will send a message in WhatsApp. So likewise, mechanical properties of a polymers also change, right, with the temperature, and it shows brittle behavior, glass-like behavior at a very low temperature, and flow behavior at a very high temperature, and at intermediate temperature, it is viscoelastic behavior, right? So elastic property at a very low temperature and viscous property at very high temperature. At intermediate temperatures, you have a uh, viscoelastic behavior, right? And these are sensitive to the rate of deformations, right? How fast you are giving a stress, right? What rate you are giving a stress. The stress rate and the strain rate is all much important in this. Okay, so this is a general comparisons between metals, semiconductors, polymers, and the composites. You see that where the mechanical properties of a polymer lies, right? You cannot compare with metals. You cannot compare with metals, but please have some idea, right? So that when you want to prepare a composite, right, then the mechanical properties of a polymer is very important, right? So if you want to improve its mechanical property, what you can do is that you can make it as a composite. Okay, so you can replace many metallic components in the structures or in automobiles or in any type of industries. Okay, so please do have always have some idea about the mechanical properties of a polymer. That is very important to mechanical and automobile and production students basically. And again, just I want to explain again, right? What happened when you apply stress with the strain, right? What happened to the strain of a material? So you know that your polymeric material is not a perfectly crystalline; it is a semi-crystalline. That is amorphous nature is also there. All right, amorphous nature is that this is amorphous nature, right? This is your amorphous nature. This is amorphous nature is there, and this is your crystalline nature, right? This is your crystalline. So you basically it's a semi-crystalline nature, right? When no stress is applied, your material is like this, right? Your material is like this. This is for a plastic nature. This is for a plastic nature, and for a brittle nature, right? You look at it here, right? This is a brittle nature. You take any polymer, basically it is a cross-linked polymer. Basically, it's a cross-linked polymer, right? So when you apply stress, nothing is happened to the material. You see that no till fracture, nothing is happening to the material. But so once it crosses 60 megapascal, right, the structure collapse, right? The structure collapse basically. The structure collapse, right? This is a brittle type of material. For example, epoxy, polyurethane, and backlight are a very good example for this material, right? I'm often telling that polymeric name. Please keep it in your mind, right? They may ask in one more questions or there's some multiple choice questions. Please be careful, right? In design. And next is that if you take a plastic material, uh, look at here, right? Okay, if you take a plastic material, what happens is that at zero stress, you're not applying any stress, and nothing is happening, right? Slowly, what happens is that you are applying a stress, right? This is under elastic range, right? Still under the Hooke's limit, right? So what happens is that when you apply stress, what happens is that your amorphous nature increases. You see that no, the area here and the area here, it keep on increasing, right? When you leave the stress, again, it will come back to this position. When you leave the stress, again, it will come back to this position, right? Okay. Now we'll go to the next stage. Still, you are keep on increasing your stress. This is your onset of necking here, right? This is your onset of necking here takes place. So at this stage, if you look at it, if you look at closely look at that crystalline part, what happens is that once the plastic region starts, then the crystalline part, right? Okay, the crystalline part orient in one direction. That is in the applied stress directions, right? So all the crystal region is orienting in one directions. That is to the stress directions. If you are applying stress in these directions, it orient in these directions. Your crystal region orient in these directions, right? So again, you are increasing a load. You increase the load, increase the stress. Otherwise, what happens is that your material grades fails at the amorphous region, right? You will get fails in the amorphous region here. You see that now, right? And your plasticity increases and your necking starts and collapse and near to fracture. That is at your tensile strength. If you look at it, your materials looks like this, right? All your amorphous chain breaks and finally about to collapse your crystalline. That is, you'll have a fibrillar structures here. Okay, so this is our behavior of plastic material and your brittle fracture. Okay. So what happened is that, when plastic region starts, your crystalline region in a polymeric material orients, right? This is that, right? When plastic region starts means then crystallinity in a polymeric material orients. Then finally, again, you keep on applying the stress, your amorphous region polymer chains breaks, right? And finally, what happens is that finally your crystalline region also breaks, and the plastic polymer fails thereafter your maximum if it attains maximum tensile strength. Okay, and each time just have to go to the toolbox and have to change it. Okay, this is your right. What happened to the temperature? Right, what happened to the temperature, stress strain behavior? Right, this we'll see in the next class. Right, probably we'll have class on Wednesday. Guys, do you have any? If you have any questions, please ask me.